All right, everyone, welcome to the problem solving part of our tutorials. Today, and in this first video, we're going to look at two problems. We're going to look at problems from section A of the book, and I'm going to show you how to deal with problems A1 and A3. So for the first problem, we are asked to consider the situation where we have G, the real numbers, with group operation addition. And the question is, to decide whether or not the collection, let's write it down, H, which is the set of logarithms of positive rational numbers, is a subgroup. And quickly, we're going to stop mentioning the positivity every single time because we know that log of a negative number doesn't make any sense. So all of our rational numbers will be positive going forward. So what does this mean? We have to check three things. We have to check the neutral element. We have to check that inverses are present in H, and we have to check closure under the operation. We recall from the chapter section, we don't have to show that it's associative because we're inheriting the operation from G, which is already associative. So for the first one, the neutral element of R is 0. Is 0 in H? That's the question. Well, can I write 0 as a logarithm of a positive rational number? Yes. 0 is log of 1, which is a perfectly good rational number. And so it lives in H. For inverses, I have to show that if X is in H, that the inverse under the operation of plus, namely the additive inverse, is also in H. So if I have a number of the form log of A, is minus log of A still in H? That's the question. The answer is yes. By writing minus log of A as log of A inverse, and remembering that that is the same thing as log of 1 over A, we see that if A is a positive rational number, 1 over A, still positive, and it's another rational number. Which rational number is it? The reciprocal. Still rational. Inverses are good. For the last part, for closure, I have to know that if I have two elements of H, that their sum under the operation will be in H. So in other words, if I have log of A plus log of B, that's not how you write a B, I need to know that this expression can be put into this form. And for this, we remember that log turns multiplication into addition. Since A and B are individually positive, and again, rational. Products of rational numbers are rational. And that handles closure. So we're done. Next, I want to show example A3. A3 had slightly different setup. For this, we have the same group, R under addition, but H is the set of real numbers for which their tangents are rational. And again, we have to check the three things. We have to check the neutral element. We have to check the inverses. And we have to check the closure. So for the neutral element, again, that element is 0. So the question is 0 a real number with the property that its tangent is rational? So 0, we have to calculate tangent of 0. And this is sine of 0 over cosine of 0. And for example, we might remember that that is sine of 0 is 0. 0 over anything is 0. It turns out this is 1, but that's okay. 0 over anything is 0. That is a rational number. So the neutral element is good. For inverses, I need to know that if x is a real number with a rational tangent, so is the inverse. And again, the inverse in this case is the additive inverse. So I have to see that if tangent of x is rational, that tangent of minus x is rational as well. And for this, we can write down sine of minus x over cosine of minus x. Sine, the minus sign can come out, whereas cosine is symmetric. And so this is minus tangent of x. Some people whose trigonometry is really good, you might just remember that. Personally, I fully admit I am not good at remembering trigonometry facts, so I like to work them out like this. But in any case, if tangent of x is rational, then minus tangent of x is just the negative of that. And so the negative of a rational number is again a rational number. Okay, for this last part, we have to say if x and y are in H, then x plus y is in H. So what that means is if x and y are individually numbers whose tangent is rational, is the tangent of x plus y rational? And what can I say? Here we have to remember our angle sum formulas, which I fully admit I would not have known if Pinter didn't print this in the text. But luckily, we're not doing trigonometry here. We're doing abstract algebra. So, Google is a thing. But in any case, the angle sum rule is tangent of x plus tangent of y over 1 minus tangent of x times tangent of y. And this is a whole big mess. But let's just sort of stare at it for a moment and unravel what's going on here. X and y are in H, and so their tangents are rational. So the top of this is a sum of two fractions. The bottom is 1 minus the product of two fractions. And the question is this resulting thing a fraction? Well, when you add two fractions, you play this game with least common denominator and so on, and you get another fraction. For the bottom, we have a fraction. We turn 1 into a fraction with the same denominator, and we get another fraction. And then we're dividing two fractions. That's a whole lot of fractions, but when you divide two fractions, you get a fraction. And so we're closed under the addition operation. And so that proves that this is a group as well.